So this is still section 6.1, and we're going to talk about models today. What ends up happening when you have a career someday, maybe this won't be your career, but somebody in here, and maybe it will. We use models to predict things. Last year, about a year ago, there was a lot of exponential models being thrown out there, a lot of data thrown out there about the virus just starting up again. And it was actually really convenient because we had just covered this when everything started happening a year ago. Anytime we want to predict stuff in the future, we use models. We can use parabolas as models. We can use cubic models. Today, we're going to use exponential models. There's two models. There's a growth model and a decay model. And they look almost exactly the same. We've got y equals, and then we're going to have a. A is the initial amount, the starting amount. So if I can't spell amount, I can. And then we do 1 plus r. R is the percent increase or decrease, depending on, if it's plus or minus, written as a decimal. So R is the percent written as a decimal. So remember to write a percent as a decimal. The word per cent means per 100. Percent means per 100. And so to write something like 5% as a decimal, we do 5 per 100. Okay, percent we write as a decimal 5 over 100. And then you can write that as a decimal from there. The quantity when we either take 1 plus r or 1 minus r, that is the growth factor or the decay factor. And then they didn't mention one thing. Maybe they mentioned it earlier and I missed it. Oh yeah, they mentioned it up here. T would be the number of years. So if something's growing, the growth factor is going to be bigger than 1. And that's what you guys learned about when you were graphing last class with exponential growth, that B value was bigger than 1. With decay, the B value is between 0 and 1. And that's what's going to happen here. If the decay factor, 1 minus the percent between 0 and 1, then it's going to get smaller. So here's a real life problem. The value of a car is going to be Y. In thousands of dollars can be approximated by the model. So here's our model. Y equals 25, parenthesis, 0.85 to the T, where T is the number of years since the car was new. We have to tell whether the model represents exponential growth or exponential decay. So using the formulas above, 25 would be what part of the formula? Ella? 25 would be which part of the formula? You can just tell me which letter if you want. That would be A, and A is the initial amount. So 25 is the A. And so did our car initially cost $25? No. Why not, Jackson? Because cars can't cost $25? Right, but there's also something in here that tells me it's not $25. Jacob? Right, it's just telling you in thousands of dollars. So that 25 represents $25,000. Okay, so that's the A. What's the 0.85? Sierra, what's the 0.85 when we compare that to the models up here? It's not just going to be the R, because for it to just be the R, I would have to see 1 minus or 1 plus 0.85, but I don't see that. So instead of just the R, it is the 1 plus R, or it is the 1 minus R. It's that whole thing in the parenthesis. Okay, now I'll write 1 plus or minus R right now, but we should be able to tell which one it is. So when I look at 0.85, that cannot be 1 plus a number because it's smaller than 1, right? So I can just go ahead and say, nope, that's 1 minus R. And then they tell you T is the number of years since the car was new. So is the model exponential growth or exponential decay, Amar? Yes, I'm sorry. What's the reason? The model is A times 1 plus or minus R to the T. That's the equation, right? And this is 25, 0.85 to the T. So 1 plus or minus R is that entire number, 0.85. If instead, if I had 25, 1 plus 0.85 in there, then this would just be the R. But I don't have a 1 plus or a 1 minus. It's already, the math has already happened. Okay. So now, Amar, I'm going to ask that question again because I know you can answer it. Is this going to be exponential growth or exponential decay according to the model? It is decay. And we can tell that because 0.85 is less than 1, but greater than 0. Okay, identify the annual percent increase or decrease in the value of the car. The increase or decrease. So what we're asked for here is the actual R value. We're asked for the R value. Nina, can you help me find the R value? I can't hear you. 0.85? It is not 0.85. 1 minus R is 0.85. So the R is what I want to know. So if we set this equation up, how can we isolate R? How can we get R by itself? Subtract 1. You're kind of quiet, hon. Is that all you said? Oh, okay. So I subtracted 1. Oops, I didn't subtract her correctly. And then divide by -1. Okay. So what is my R value? 0.15, 0.15. Now, I want to know the annual percent increase or decrease. So 0.15 is what percent? 15%. Right? Because 0.15, I'll write down here. Oops. 0.15 is the same thing as 15 over 100. That's 15 hundredths. Percent means per 100. So 15 is the percent. And then estimate when the value of the car will be $8,000. So when will the car value be $8,000? We're going to put 8,000 in the Y spot. Nope, we're not. I lied. You guys can tell me what I did wrong when I write this out. You already know, Jackson? No, we don't have to make a t-shirt. But what did I do wrong? I'm filling 8,000 in, but I did something wrong with that. Tessa? The model is in thousands, so I don't want to write 8,000 there. I just want to write 8. Yes. Otherwise, we're going to have a way different number. Now, so now at this point, we could make a t-chart, but that's a lot of work. I'm going to use my calculator. We're going to use our calculator's t-chart, okay? So what I want you to do is we're going to go, we're going to go and we're going to type in, I can find my calculator. Here it is. We're going to go to y equals get rid of my old stuff. Okay, we're going to go to y equals this top button here. It's red. The buttons I pushed turn red if you're trying to follow along and didn't see where I pushed it. Y equals, we're going to type in the model. We're going to type in 25 parenthesis 0.85 close parenthesis caret, so to the, and instead of typing a T, we're not going to type a T. We're just going to use X on our calculator. Okay? And then we're going to go to our calculator's T-chart, which is the table. So you do second graph. And we are going to look in the Y column to see when approximately it goes to 8. So we're going to look for when the Y goes to 8. And it's going to be approximately. We will eventually learn how to do it exactly, but not today. So about how many years before it's worth $8,000? 7 years. Yep, right there. At 7, it's worth 8. That's 7 years. Okay. Oops. All right, example number 3, we're going to write an exponential model. In the year 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. Write an exponential growth model giving the population Y in billions T years after 2000. Estimate the world population in 2005. So I'm going to go back through. We're starting in the year 2000. The world population was about 6.9 billion. So this is part of our model. What part of our model is the starting? Emma, what part is the starting amount? In the model formula. Oh, no, that's the number, but what letter? Sorry. A. That is the A. Yes, correct. And then during the next 13 years, the world population increased by about 1.18%. So what I want you to know is we're not going to actually use this 13. They're just telling you we observed this happening over 13 years. We're not going to actually use that. But what they noticed is they found a rate. So 1.18 is percent. That is not our R value yet. Our R value has to be the percent over 100. Okay, we have to take that percent and put it over 100. Then it becomes the R value. So our R value is going to be 1.18 over 100. And if you want to decimalize that, you can either use your calculator, or what does the dividing by 100 do to the decimal point? Goes to which way is that? I'm not good with my directions. Left. So we'll have 0.018, right? Yeah. So that's the R value. And then for estimating the world population in 2005, what is our T value going to be? Brooke. Sorry. We're going to have to estimate the world population in 2005. So what will our T value be? How many years would that be? 5 years. So we're going to write our model. We're going to have Y equals our A, we said was 6.09. Oh, there was one more thing I forgot to call attention to. Which model are we doing? Are we going to be doing plus, or are we going to be doing minus for our model? Jackson.
For the decimal where it's 0.018, isn't it 0.118? Is it going to the left?
2 spots.
Oh, okay.
2 spots, because it's we're dividing by 100, so it'll move it 2. But Jackson, can you also answer this question for me? If we are doing increased and we are doing growth, am I going to use 1 plus or 1 minus? We'll use 1 plus. So we're going to go 1 plus our rate, 0.018 to the T. So that's our model. We can simplify our model. I'm going to simplify it just a teeny tiny bit. Y equals 6.09 times 1.018 to the T. So that is our model. And then it also says estimate it in 2005. So we're going to find the Y when T is 5. You think I want you to do that by hand? Most definitely not. So use your calculator. So I'm going to do 6.09 parenthesis. Oops, why did I do 8? 9. 1.018 to the 5. And approximately 6.658. That's what I'm going to go with. 6.658 billion. Okay. And then estimate the year when the world population was 7 billion. So we're going to make it 7 equals, and we're going to set it equal to our model, 6.09, 1.018 to the T. How can we estimate this? Hint, we did it on the first question as well. How can we estimate this? Hint, you need technology. What? Say it again, Sophie. Do the Y equals. Yep. Let's go to Y equals. $6.09 times 1.018 to the, and I'm going to have to use X, and go to our table. So approximately what year will the population have been 7 billion? Warren? In the 8th year. So what year is that? Okay, so 2008 would be the year. Do you guys know how many people are live in the world today? Does anybody know? Okay, let's Google that real fast. About 7.674. Let's see if that works with our model. So what would I look for on my calculator to see if, oh wait, that's 2019. Seven 7.8. Let's see if that works with our model. So what number do I have to go to on the X? What number will I go to on the X? What? 21, right. And you can actually jump there. Just want to show you. If you ever need to go to like 100, you don't want to just arrow down 100 times. So you can do second window, which is table set, and you can tell your table to start at 21. And then I'll go back to my table, second graph, and there it starts at 21. So is the model accurate? Yes. Oh, I have the decimal wrong? I just typed it in wrong, is what you're saying? Yeah, I'm sorry. So was our answer wrong about 2008? Oh, because he was looking at mine. Oh, let's go back and fix that. Thank you for saying something. Everybody else, where were you? Okay, so let's go back. I'm going to make my window start again at 1 or 0 or wherever it was. I don't remember. 1. Okay, so now that does look like different numbers here. So yeah, at 2012 should be the correct answer. I apologize for that. Oh my gosh. Miss Criswell, how could you do that? I thought you were a robot and never made mistakes. Right? That's what you guys thought, right? Okay, sorry about that. And then we can go back to looking at 21. To see how accurate it is. It is pretty darn accurate, isn't it? Isn't that crazy? Like, that's why math right here, why math is really important. Because we have to plan for having almost 8 billion people on this planet. We got to make plans for that. You know, where are all these people going to live? How are we going to have enough power, food, everything? We got to plan ahead of time. So using models will help us know at what point we're in trouble. You know what they also use models for? Global warming and the sea level rising. At what point will grandma's house be underwater because she lives in Florida, right? Okay. Example 4, I'm cutting out this year. Bye. So 7's gone too. I cut that out of the assignment. Okay, and then the last part of this, I think it's the last part. Yeah, the last part of this is just talking about compound interest. If you were to put your money in some sort of interest growing account, which there's not a lot of that these days, but if you're going to put your money in something, we're going to earn interest, you kind of want to understand what's happening. So this is pretty important as well. So this is called compound interest, and it's interest that's paid on money that you put into the investment. So the first thing is a vocabulary word called the principal. The principal is what we call the initial amount. Or the original amount. The principal is the original amount. And it says, and on previously earned interest. The interest earned is often expressed as an annual percent. So annual means yearly. But the interest is usually compounded more than once per year. So the exponential growth model, y equals a times 1 plus r to the t, must be modified for a compound interest problem. So what's happening is we have a yearly interest amount, but the investment actually does parts of the interest throughout the year, compounds it more than once. So this model is going to be tweaked a little bit. So if we have a compound interest situation, this is the model that we're going to use. So it's almost the same, except we have this extra little n thrown in there. N is going to be the number of times per year. Number of times per year that it's being compounded. So here's the formula. A is going to be the new amount. That's after time. The new amount, that's after time has passed. P is the principal, which is the initial amount. R is that percent as a decimal, same that it was before. N is the number of times compounded per year, and then T would be the number of years. So all of that's the same that it was before. It's just we're using A and P instead of Y and little a. Okay, just different letters, but you're still going to put the same stuff. So here we've got you deposit $9,000 in an account that pays 1.46% annual interest. Find the balance after 3 years when the when the interest is compounded quarterly. So this word right here, I want to draw attention to. This word could change. This says quarterly. Who can tell me how many times per year quarterly is? Nina. 4. And then there might be other words. I just want to throw out some other vocabulary words in there because I know people ask every single year, like, how many times is this per year? What if we did semi-annually? How many times per year would that be? Semi-annually. 2. Tri-annually. I think that's a thing. I think it is. I'm making it up, maybe. Tri-annually. Guess. Emma? 3, yeah. I don't know if that's the right word, but I think it is. So quarterly we just got was 4. Monthly is a hard one. Who can tell me how many times if it's monthly? Oh no, nobody can. Somebody said, I don't know who said it though. 12. All right, now I'm going to get harder. Weekly. Tessa? Good, 52. That's a life skill. 52 weeks in a year. Daily. Jackson. 365, unless it's leap year and then it'd be 366. We're not going to worry about that though. Hourly? $365 times what? 24. 8760. Should we go smaller? No, let's keep going. All right. So if you come across a word and you're not sure, if it's not one of those that I threw out here, I can't really remember right now if there's any others that you'd see. But if you come across one and it's not one of these, just ask, okay? I don't want you to miss the problem because you hadn't seen that word before. Now, if you're at home, you can just like Google it. I mean, if you see one on like a test and you can't Google it, okay. I hope you don't email me to say, how many weeks are in a year? Because you can find that information. All right. So we deposit $9,000. $9,000 is the principal. That's our P. In an account that pays 1.46%. So that is not the R. How do we find the R? We divide it by 100. We do 1.46 per 100%. So our R value is going to be 0.0146. And then we find the balance after 3 years. So that is T when the interest is compounded quarterly. So that is our N. So we're going to stick all this stuff in. A equals 9,000, parenthesis, 1 plus. Now we do our rate, 0.0146 over the N value, 4. And then we go to the N times T. So I've plugged everything in. You literally can just plug all that into your calculator and it should work. Sometimes I will just, simplify one tiny little thing and type that in my calculator. Oh my gosh, Amar, what did I just do? Okay. So I'm going to type that into my calculator. If you have the new calculators, remember you have a way of making fractions easily. So I'm going to do 9,000, parenthesis, 1 plus alpha y equals enter. And then I can type it in as a fraction. If you can't type it in as a fraction, I will also write it a second time on here. I'll type it a second time, pretending I have the older calculator. So if you have the older calculator, then you could do 1 plus 0.0146 divided by 4, and it will be fine. To the 12. You could do it that way. Yes, dear.
Why did you multiply 4 times 3?
Because that's in the formula. The formula says N times T. You see it? It's teeny tiny. So I got $9,402.21. Now here's two more things that people don't quite understand vocabulary wise. There's the word balance, and then there's the word interest. This one asks for the balance, but I will find both so you can see what both are. So the balance is how much is in the account. The balance is now 9402.21. The balance is the A amount. Okay. If you're asked to find the interest, that is the balance minus the principal. That's take that 9,402.21 and subtract off the original 9,000. So that would be only the amount that you earned extra, 402.21. Okay. Sometimes I'll ask you for balance. Sometimes I'll ask you for interest. So you should know the difference between the two. Okay, we're going to do one more thing before we take our break. And if you haven't downloaded it yet, it is on today's module. It is called Investigating the Natural Base E. Investigating the Natural Base E. And as you're opening it up, we're going to invest $1 for 1 year at a rate of 100% compound interest. So we're doing this so that every single number is 1. Okay, we're investing $1 for 1 year at 100% compound interest. Bless you. So my R, we take the percent and we divide it by 100. So our R value is 1. Our T value is 1. Our principal is 1. So I'm investing 1. I've got 1 for my T. I've got 1 for my R. Everything's 1. So it's not a real life situation, but we're going to see what happens. We are going to, excuse me, we're going to conclude what will be the value eventually. Okay, let me start that again. We're going to up the number of times this is compounded per year until we get to infinity, which we can't do. So we're just going to guess. We're going to see what it gets closer and closer and closer into. We're going to see what it approaches. Okay? And you will need your calculator. So for yearly, we're going to invest $1 at 100% 1 time a year to the 1 time a year multiplied by 1 year. So basically for yearly, everything's 1. I'm plugging it all into the formula. And what do I get? Gosh, you don't need a calculator for this one. What do I get? Ashton, what do I get? 2. Excellent. Okay. Now, for semi-annually, we're going to have $1. We always do 1 plus. It's 100%. Semi-annually, and is now 2. And we're still doing 1 year. Okay? So now perhaps you want to start using your calculator. I'm going to call on you, so you better be doing it on your calculator. If you don't have a calculator, they have this thing called the internet that has calculators on it. And Aya, when you get that answer, I'd like you to tell me it. I don't think you typed it in right, hon. Oh, you did 3. 2.25, that is correct. Okay, the next one is quarterly. So we're going to do 1. Oh, for quarterly, what is n? For quarterly, what is n? 4. So we're going to do 1 times 1 plus 1 over 4 to the 4 times 1. Holland, I want you to give me that answer. And I'm going to go 2 more decimals, okay? 1, 4. Are you guys working ahead? Or are you not getting it? Oh, that it goes to a fraction? So hit math and then decimal, which is number 2, and then enter, and that'll fix it. It won't do that. I don't think it's going to do that from now on. It was just that one question. Yeah. All right, monthly. Monthly, we've got our n value of Ketsia. If it's monthly, what's our n value? 12, good. So I'm going to do 1 times 1 plus 1 over 12 to the 12 times 1. Evody, can you tell me the number? 30. Yeah, 4 decimals. Okay. So daily, n is 365. So we're going to do 1 parenthesis 1 plus 1 over 365 to the 365 times 1. Ari, did you do that one? Good. 2.7146. All right. Hourly. What was that number again? 8 something. Does anybody have that? 60. Okay. Thanks. I don't want to look it up. All right, so then we're going to do 1 times 1 plus 1 over 8760 to the 8760 times 1. Sierra, where's your calculator? Quit leaving it in your locker every single math day. Are you doing it on the computer on a calculator? Tell me if you got this one or when you got it. This section is definitely a calculator section. 2.718, one more decimal, 1. Okay. All right, every minute. So for every minute, we're going to take that 8760 and multiply it by 60, which is 525,600. Now we're going to replace that. Are you guys aren't retyping this equation in every single time, are you? Are you using the previous one and just changing it? Thank you. You're not retyping it from scratch every time, are you? Not anymore. I should have said that earlier. I mean, you can. It just takes a lot of extra time. Joel, do you have a calculator open? Are you doing what, hon? You don't have one open on your computer? Do you have one open, Warren? Do you have a calculator open on your computer, Warren? Maybe get that so you know how to use it or type it in correctly. All right, I'm going to speed this up a little bit. That is 2.7183. So every second, I'm going to multiply by another 60. I know that's like so hard to do on your calculator, right? Just kidding. So that number is 3153600. 1 times 1 plus 1 over 3153600 to the 3153600. Again, I'm not retyping this every single time. I'm just changing the number in the bottom and the top. Yeah. Oh, yeah, you're right. Thank you for saying that. I put it there, but I didn't copy it over, did I? I need you guys around to make sure I don't make mistakes. Thank you for that. I don't think I would be a very good statistician, because I make too many silly mistakes. Okay, the next one is a larger value. So we need to pick something larger than this 3153600. How about we just add in another, so you don't have to retype everything. This is just my idea on the spot. How about we just do another 0 on that, or another 2 zeros on that if you want. How about just another 0 on this one? So you just have to go in and add one more 0 in it. So we'll have 4 zeros. Just make sure you put it on both of them, though. And then a larger value. So maybe another 0 on, maybe another 2 zeros on. Oh, I'm going to add 2 zeros. I'm going to get really big. What'd you guys get? Did you get this? Again? So what do we think? As n is infinity, what is this going to approximately be? Look at the answer. What is it getting closer and closer and closer to? I didn't put all the decimals, but what's it getting closer and closer and closer to? Sophie, what is this number going to be if n is infinity? No. What is this number going to be if the number that I plug in is infinity? Tessa, what's this number going to be if the number I plug in is infinity? 2.7183. Okay, approximately. We can never get to infinity, so it won't actually be that exactly. But now I want you to do one more thing on your calculator, because the title of this was investigating the natural base E. There's one more thing I want you to do on your calculator. I want you to do, where is it? I'll find it here. I want you to do second, and then there's this button that says ln, but above it, it has an E. And then it's going to open up a exponent. I want you to put a 1 in that spot. So I want you to do e to the first power and hit enter. What is the answer? 2.7183? This is called E. And what we did today is how we get E. E is a number just like pi. As it is irrational. It's got all those decimals that go on forever. And it comes up in math, especially in exponentials. And so this is something important. We will use it a little bit in algebra 2. You would use it more as you get into higher level, into higher level math as well. But it's called the natural base. And we discovered that number by doing something that we just learned. Okay? So I'm going to stop the video. We're going to play a game. Sound good? All right.